So hello, good morning everyone. So we'll start again the operational research, and our topic today is about queuing theory, right? Let's go to Lentera. Okay, so this is what we discussed the last time. Okay, so we start to go into the detail. Last time we already uh, talked broadly about the management and queuing rule of thumb and how to do the survey, right? And then we go more detail about each type of queuing. So here is the single server queuing theory. So this is the Kendall notation is MM1, that means Markovian 1. Markovian means the arrival is Poisson, right? And then the service time is exponential. Okay. 1 here represent the number of server. Okay. And yeah, this is the Kendall notation for the queuing. Yeah. So M means Poisson. Okay. And you should remember that the steady state that we are discussing here, very simple formula because this is actually in steady state. Right? So when we are in the transients, so the problem will be dynamically changed. So when you do simulation, you will use transient period, and then if you simulate very long time, then you can get the steady state result. So the queuing theory only discuss steady state part, not the transient part. Okay. So what is the meaning of steady state here? Meaning this is the long-term solution. Okay. So if we repeat this for a long term, infinite time, then this is the actual solution. Okay. And these are the common measurement of effectiveness of all queuing. So you should know the symbol. Okay, so we have a P0, that means probability with 0 customer. Okay. Pn means probability that there are n customer in the system. This is a little bit inconsistent in symbol. Pw means the arriving customer has to wait. Okay. Pt larger than T, T capital, that the customer will wait more than T unit of time. Okay. And WQ means the average time of customer spent in waiting line. Okay, W means the average time customer spent in the system. That means in the waiting line plus being served. Okay. The same thing with the LQ and L. Here is the average number of customer in the waiting line and in the system. Okay. With this, so these are the assumption of MM1. Okay. Later on, we will try to remove a few of these assumptions one by one using different model. Okay, so one is the population is infinite. Okay, the customer arrive and enter facility individually, not as a group. Okay, so the recent queuing theory actually is about group. Okay, so of course, we don't use that in our class. Yeah? But if you are interested, you can study about it and do research. Yeah? And arrival rate follow Poisson distribution. Service discipline is FIFO, meaning first in, first out, right? And then the customer must stay in the system until their service is complete. Yeah? No parking, drainaging, or choking. And then waiting area is unlimited, yeah? Infinite. Okay? Later we can remove this assumption. And then service time is exponentially distributed. And this is very important assumption. A service rate is less than arrival rate is less than service rate. Okay. In all Markovian, okay, any random distribution, basically the arrival rate must less than service rate. Yeah? And unless DD 1. Okay. So And then the customer in front is immediately served without walking time consideration. This, again, any model, what you need to discuss is actually the assumption. Okay, why? Because it is the assumption. If the assumption is correct, then the model is correct, right? Okay. Model is not the true reality. Okay, model is just simplified version of the reality. You should know that. So then we need to discuss the assumption, because the assumption is the one that make the model true, right? Okay, so with this assumption, these are the formula. Okay, the formula is easy. You don't need to memorize this formula. Okay, so anyway, I built the calculator in my website, so you can just use. If you really want, you can also use this in Excel. Okay, you just simply put in Excel. Utilization factor, yeah, it must be less than 1. Yeah? If the utilization factor is larger than 1, then the waiting line will continue to grow without limit. Remember, this is steady state, yeah, not transient. That means it's already in the long term. So in the transient, there is possibility that there is an empty time. There is a certain time duration that there is no customer arrive, right? But this is in steady state, so that possibility is not exist. Okay, so again, this is the formula you can just use. Okay, if you want to use this formula, what you will use first? Number 1, you will calculate rho. Okay, rho is lambda over mu. What is lambda? Lambda is the arrival rate, yeah. Mu, service rate. Okay. Be careful, mu is service rate, not service time. Okay, that means if you have service time, you need to calculate 1 over service time. Yeah, mu is 1 over t. Okay, once you calculate the rho here, you can calculate P0. Okay, after you calculate P0, then you can calculate P and PW and so on. Yeah. So here you see the WQ depends only on lambda and mu. Yeah. W depends on mu and lambda again. Yeah? The same thing with L and LQ. Okay. So you can check this and you can use. And this is, I did not calculate everything in this, even though we have the formula, we did not calculate this P T larger than PT, customer has to wait. I did not even calculate that. Okay. So only a few important performance that I put, up to probability of idle. Okay. But at least you know what is the meaning of queue intensity, queue utilization, right? Okay, so you want to practice, you just put this number there in the website, okay, or you want to calculate using Excel, is up to you. So the point here is, if you input this number, okay, and you will get LQ, for example, 2.25. Here you will see this is not actual, there is no person of 2.25, right? So number of customer is person in here. So that means this is actually average. Okay, not the real person. On average, okay, you will have 2.25 customer waiting in line. Okay, on average, okay, you will have 3 customer of the 3 people in the system. Okay? And then on average, they will wait for 4 minutes, including in the system, and in the waiting line is only 3 minutes. Okay. Now, because you know P0, okay, and formula of Pn is dependent on P0. Okay, so P0 is 25%. This is the idle probability of idle of the server. Okay. And from from here, if you know P0, you can calculate Pn. Pn is P1, P2, P3, P4 until P, and so on. Okay? So this Pn is based on this formula, so you can calculate the probability of number of customers in the system. Is it clear or not? Okay, so, and you also can calculate the weighting. Yeah? What is the probability that person will wait in the system? So 75%, right? Of course, this is 1 minus the P0, right? Anyway, so, and this is, what is the probability that the customer will wait more than 5 minutes? So 28%, right? Now, in this practice, okay, instead of 0.75 and 1 with this customer per minute, I multiply by 60. Okay, I multiply by 60. So what we get here? Of course, 60 times 0.75 is 45, right? And then 60 times 1 is 60. So that means they are actually the same thing, okay? But the unit change. Okay? From customer per minute now become customer per hour. The question is, will the MOE change? Okay? So you can try. Okay, I use Excel here. You can also try in the website. Okay, and you see here, they are actually the same. Yeah? So regardless, so the point here is that it's not about the lambda and the mu itself. It's about the ratio of lambda and mu, right? Because even if you multiply by the scaling factor, which is the same scaling factor, you will get exactly the same result. Of course, that result now become per hour, so that means you need to put this into minutes if you want to see the same result. Okay. So here is I try to calculate over different units. Okay. Again, you will see L and LQ are exactly the same, of course, and only the W and WQ is different. Yeah? That difference is actually just changing of the unit. Okay. Next, the next question is, okay, I have only single server, and I cannot add additional server because I get that will be costly to me, right? So, but can I improve that? Okay, so you can improve. How you improve? Of course, you improve. One of the way is to change the material, the actual service time. Okay, you separate the material from the information, right? So one way is to employ an order filler, okay? Or certain website, they can take the order, the information part of it, okay? And then based on that, you can actually improve. Yeah? So say the service rate, okay, instead of 60 customer per hour, now becomes 75 customer per hour. So just improve 15, yeah? Actually not so much improvement, but let us see what is the actual improvement in the performance. Okay. And you need to check that the utility is less than 1. Okay. And you can see here, the performance is actually improved, right? A while ago was how much? 4 minutes, now become 2 minutes. Yeah? Right? A while ago was 3 minutes here, now become 1.2. So if you look at the performance improvement and you look at the input improvement, yeah. So we improve in terms of service rate here from 1 now become 1.25, right? So that means improvement in the service rate is how much? 25%, correct? Right. So 25% improvement in the service rate. How much improvement in the delay? Double, 100%. Correct? So with this, you can see queuing is actually non-linear. Yeah? Small improvement in the input, okay, will produce large improvement in the output. Can you see that? Any question? Okay, so after that you can also check everything else if you want to know. Okay, so from here we can also calculate, for example, look, this is the current situation. We already improved. Okay, lambda is 0.75, mu is 1.25. Okay, and then you said, okay, we attempt to improve the service rate through training of server. Okay, the management decided that on average, okay, now this is the management decision. Okay, that 99% of the customer must be served within 5 minutes. Right, this is management decision. So then the question is, okay, if you want that decision, right, what is the implication? Of course, the target service time in this case, yeah, must improve, right? So how much improvement? So what is the question here? I know the performance, okay, 99% of the customer must be served within 5 minutes. And then what I can control is not the customer, but I can control the service rate. Yeah? So how do you control the service rate? Improve the training. Okay? So we calculate that. Okay? This is the formula, right? The P is 99%, and that formula depends on mu. Then you can calculate the mu. Okay, you get 35 seconds per customer. So then the training must be improved. Okay, you let the server train themselves so that on average they can get this result. Is it clear or not? So meaning that not only you know the input, you get the output, you can also control. Yeah? If you know the output, you can predict the input, right? So, okay, so on summary, okay, the queue length and waiting time will grow to infinity if the average, if the arrival rate is higher than the service rate. Okay, so if you look at the formula, okay, actually the MOE, the performance measurement, is derived from the probability of MT and K customer in the system. And please remember that changing the unit of the input does not change the MOE. It's the ratio that matters, not its unit. So this is the implication. What is the implication of this? At this point, not so much, but later, and when we do MMS, it will have a very big implication. Okay, let me go to the next slide of MMS. So MM1, no problem, right? Is there any question?
No, sir.
Okay. So let's go to the second part, which is MMS. So, okay, which one is MMS in this? Which one is MMS? This is the most important part here. Okay, when we said MMS, okay, clearly the first part here, this is what? This is MM1, right? This drawing. Okay. How about this one? Yeah. This is
That's MMS.
that is MMS. Okay, this is exactly MMS. Okay? Single waiting line and then multiple server. Okay, parallel server. This is important. Huh? Okay, and this is what is this? This is MMS.
MM1.
This is exactly MM1. Okay, n times MM1. Be careful. Okay, if you don't know that, so you will calculate wrongly. Right? So this one at below here is actually three server of MM1. Okay, when we said MMS is actually in the middle here. Is it clear or not? Okay, so without knowing that, you will calculate wrongly. Okay, so this is everything is the same. Important part here is what? Assumption. Right. So this assumption, the customer join a single waiting line. That means what? Single waiting line is this one, single waiting line. Clear, yeah? Next. Service time exponential distributed with the same average service rate. So, look, this is the assumption here. All servers are identical. Oh, this is an unreasonable assumption. Yes, but this is what we assume. Don't forget that. Okay. Of course, the arrival rate is less than service rate, but be careful. This is not the service rate of one, but system service rate. System service rate. Okay. All the others are the same as MM1. So, what is system service rate? Oh, look. Now, instead of rho, okay, now I use 1 over S. Okay, so the intensity is still the same, rho, right? But utilization factor is 1 over S. This is the one that must be less than 1. Not the rho less than 1. Of course, rho can be any number. But as long as the U is less than 1, that's fine. Now, look at this. P0 formula is 1 over this value, which is the summation of rho exponent to n divided by n factorial, okay, and then rho exponent s. S is the number of server, okay, and then s factorial. So the formula is rather complicated, isn't it? Okay. The same thing with the probability to wait. Now I put it as FQ here. Okay. This is also a complicated formula. Now again, the Q length become much more complicated with factorial here. Okay. The average system length is just LQ plus rho. And then the weighting in Q, what is this? This is Little formula, John Little formula, right? So again, we use the John Little formula here for the weighting in the system. And then this is probability of weighting, and this is probability of n unit in the system. So again, I already create the calculator. You just input there. Not everything I put out. Okay, so probability of weighting I did not put out. Probability n unit I did not put out. Okay. So say now if our burger system a while ago, now we want to get the second server. Now it's one server. Now we have two server. Okay? So that the customer can be served simultaneously. So again, the arrival rate is the same, 0.75, and service rate is still 1 customer per minute. What happened? Okay, and here, because I use Excel, what happened is I need to calculate for n. So I need to calculate for n. Say I put maximum until 10, for example. So I need to calculate one by one for each n, right? Because n here, you look at the formula is a sigma, so Excel cannot do that. So we need to calculate one by one into another table. Okay, and then from this result, we put it into P0 here. Okay, so computation is a little bit more complicated. Okay. Do you want to practice this, or we just skip the practice and continue? Anyway, the calculator is already there, right? So probably you can just use that calculator. So look at the numbers. I use the same value, 0.75 and 1. If the number of server is 1, what happened? What is the average waiting time in queue? If the number of server is 1, how much? How many minutes? Oh, can you try? Can you try a calculator? Where is that? Oh, here, you can go to this website. Okay, so you try. Arrival rate is 0.75 and mean service time is 1. So what is the average waiting time in queue? Anyone?
Wait, sir. I'm still typing in because my internet's quite slow. I changed to my phone.
Okay.
Wait, so arrival rate is 0.75?
Arrival rate is 0.75 and then service time is 1 and then number of server is 1. So what is the delay?
3.
3. Now if the same thing, yeah, now you increase the number of channel, meaning the number of server you increase, now become 2.
Oh, 0.1.
0.16, right? So now what you need to check is the percentage, okay? 0.16 divided by 3, how many percent?
5.
Or 3 divided by 0.16, so that you can see. Okay. So 3 divided by 0.16, how much?
18.75.
18 times, okay? 1,800%.
Oh, that's a lot.
That's a lot. Okay, improvement is 1,800%. Okay, so adding server is costly, but the improvement is drastic, isn't it? Compared to improvement of the service time a while ago, yeah. So now this graph is very important. You know row, right? What is row in here? Rho here is lambda over mu.
Mm.
Okay. Rho here is lambda over mu. So lambda is the arrival rate, right? Mu is the service rate. Okay. Now, if you input that into the formula, okay, and then you plot, okay, you will surprise that the plot is not one line, but multiple lines like this. Why? What is the meaning of multiple line like this? This is L, this is the Q length. Okay. Why is not one line, but multiple line like this? What is the meaning of this multiple line? And then each line here is close to discrete number, right? Can you see? Close to. It will go up until 1. It will go up until 2. It will go up almost 3, right? It will go up almost 4, right? Go up almost 5, and so on. Can you see? What is
Mm.
thing? This is very important graph. Instead, you have one formula. Remember, the formula is this one, right? Or where is L? Yeah, this is the L, right? This one. So L or LQ is just up, right? So it's the same formula. Okay. But instead of one line, okay, if you graph it, it will become multiple line like this. Oh, and then approaching almost 1, almost 2. What is that? Give me your thought. What is the probable meaning of this? Divi, any idea?
Mm.
Joy, any idea?
L is the length, right, of the waiting line.
L is the queue length.
Q length.
Queue length means the number of customer in the system.
Rho is the utilization factor.
Rho is not, is the intensity. Rho is the intensity, is the lambda over mu. Right. So what's the meaning? Okay. So this is very important. Why I said this is very important? Because if you understand this, you understand the meaning of MMS. Okay. So basically, imagine that you have only, it's not random. If your queuing is not random, it's DDS, for example. Okay. What will happen? Compare it with that. So if your customer, okay, is going above, yeah, if your row, meaning your arrival is larger than the service rate, yeah, the arrival rate is larger than the service rate, okay, it will go up and up, but look, it will go up at to certain number of customer. Sorry, number of server. So this is actually, each line here is number of server. Can you get it? Okay. If you have only one number of server, it's go up, okay, up to infinity, right? Then you said, look, I cannot make it up to infinity, so I need to improve with the second server. So that's why I get a new line here. This is a screen. What is this screen? This is the number of second server. Okay, so that means if I add the server, suddenly from here going down there, okay, the queue length going down there, and then say the number of arrival rate improve, the demand increase a lot. Okay, say the service time still the same, right? So the demand increase a lot, so row increase up to certain point, it will again go to infinity. What is this? Go to infinity because it reached the row 2. Yeah. And then at this point you said, look, this is too high already. I need to improve by adding new server. So when you add new server, you go down from this screen, going down to this red, yeah, the queue length. Okay, and then again the arrival rate improve again until this is a server number 3, right? Three server. Yeah? This is 4 server, 5 server, and so on. So every time you add the server, when the demand increase, okay, it will go up to infinity again. Clear?
Yes.
Yeah. So there is a limit. Okay. So increasing the number of server does not mean that improve. Say, for example, like the road. Yeah. Oh, the road you put only one lane in the road, right? And then become congested, and then you add another lane, right? That the number of lane in the road is actually the server, right? Okay. So and then you add another lane, okay, and then the demand increase again, right? Oh, getting more congested again, and then again you add another lane. So eventually, okay, when the demand keep increasing, yeah, so yes, it will go to infinity again. Okay? If the number of lane does not improve a lot, okay, so eventually it will go to infinity again, and then you said, okay, I need to add one more server. And look at this, the more server that you have, for example, you are already having 8 server here, this blue line here, okay, and then you are already 40 number of number of customer in the system, yeah, is 40, yeah, all the time, and then suddenly you add one more server, it drop a lot, right? For the same row, it will drop a lot here. But when you increase the demand again, it will go up again to the infinity. And that drop a lot is compared to this drop is actually much higher here, right? The drop of improvement. Yeah, this drop means the improvement of the system, isn't it? Is it clear or not? Okay, tell me what you just learned. I want to understand what you understand. Livi.
So, you mean from this graph or?
Just from this graph.
Okay. So the line which go up means the like how many the server, like amount of
Each line
users.
here is the number of server.
Yeah,
Yeah.
and then it will goes up as the length of the queue getting higher to the
Mm.
certain number,
Mm.
and then the number of the the server can increase as the system is it- as the system is getting bigger.
What does that mean?
I mean, it can increase the number of the server can increase to until the the wait the waiting line it's
No, no.
um
The waiting line will go to infinity, okay, if you keep increasing the demand. Okay. The meaning of this line going up here mean rho is increased, right? Going to that
yeah.
direction. Okay. How rho will increase? Rho will increase if you keep the service rate constant and the demand increase. The rho is lambda over mu. If mu is the same and then lambda increase, so rho increase, isn't it?
Hmm. Number yeah.
Right? I will write it. So rho equal to lambda over mu. Okay. So if mu is equal to 1, okay, constant, right? So now you increase the lambda, okay, then rho will also increase, yeah,
Hmm.
okay. So
Hmm.
this formula, okay, this this happened because actually here, the utilization factor, you see, the utilization factor, okay, depends on divided by S here. That's why the line is actually one by one depending on the number of server. Joy, you want to say something? I cannot hear. I didn't see us.
Sorry. Wait.
Yes.
So if the arrival rate increase, so the waiting line will be increase also.
Waiting line.
Yeah, the waiting line.
The waiting line is the L. Yeah.
Yeah.
If your remember rho is equal to lambda over mu. Okay.
Yeah.
If the mu is constant and your lambda increase, the rho will increase, right? The waiting line
Yes.
on the row, can you see that? And the number of server, right? So if the row increase, if the row increase, the waiting line will increase exponentially because that depends on the row is actually exponential here.
Mm.
Okay, it's actually exponential. Okay, the same thing here. Because delay. This is the delay, right? This is waiting in queue in delay, right? So the delay depend on the LQ and L, right? And the L is actually that formula a while ago. So you can there is a very close connection between the queue length and the delay in this case.
Okay.
Okay, I hope that's clear. Next, yeah, this is okay for the same demand and the same number of server. Which one is better? Yeah? Single line, yeah, or multiple line like this. Okay, again, how to model using queuing theory. Yeah, so. You can try, okay. Uh, you can plot the row versus W and row versus L, okay. And then mu is 1, and then let's say lambda is equal to rho, and then you try uh, for single line and then for multiple line, okay. So for multiple line, each line have arrival rate the same as lambda over S, right? And then each line is 1 mm1. So, and then the question is, what happens if you increase the number of server to 10? Can you practice this? Just, you have the calculator there already, right? You just input the number, okay? And then report to me what is your experience about this. I think this is important to see.
Okay, so can you hear me, sir?
Yes, yes.
So we assume the
You can
both.
you can assume anything. So in this
Okay.
case, I can assume mu equal to 1. So that easy to compute. Right? And then with that, I can increase lambda. Yeah, you just create a table, okay, in Excel, and then you start calculator, and then the result you can just input into that table that you created. So compare between MM1 and N times MM. Oh, so sorry, N times MM1 and MMS for the same number of server. So you can put number of server 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You can compare 2 server with 10 server, for example. So which one is better? So you increase the row, okay? You want to share your screen once you finish? This is how you do research, right? So even if you have the formula, okay, so if you don't do research about it, you will not really understand the formula. Okay, so I can give you the formula, but you're supposed to understand that formula. What's the meaning of that formula? What is the implication in our life? Okay, so this is the example on how you do some kind of little research based on that formula. So you input the numbers. So 2 server and 10 server, only two category. So they change actually or no change? And which one is better? Okay, you only get the queue length and the delay. Okay, anyone want to share the screen? To plot, you don't need to put so many intervals, so you just put any, maybe 3 or 5. You know, so practically you only need six numbers. Hmm. You can share your screen. Hmm. You want to share your screen, Davy?
Yeah, but I'm not finished yet. I'm still with let me share it. Here. How to like
Oh, no. Don't do this. What I mean is, you create a table. Okay. You use the calculator that I created, right? You create a table.
oh
Okay.
so the table is for the only the L and the row.
Correct. You only put the table of row, okay, and then from L and then W, right, and then S,
And then
right? Okay. So now you can put row equal how much you want to put. Say row equal to 0.2, for example. increase row 0.5. Okay, so row equal to 1, for example. So, okay, so now depend on your S, your number of server, right? So if S is 2, so this always 2, 2, 2, 2. So in that case, your row can reach up to 2. So you can 5.
5.
You cannot make row 5 if your server is only 2.
Oh, so 2, only 2.
Maximum is 2. In fact, you cannot even make 2. So 1.5 you can. Or 1.2 you can. Right. And then for okay. From here, if you know the row, and row is equal to lambda over mu, right? So say assuming mu is equal to 1, then lambda is equal to row, isn't it?
Yes.
Yes. So now you input in that calculator, okay, lambda is equal to,
It's this one.
use the MMS, not the MM1. Use the MMS. Yes. Okay. Right. Okay. So this one, the arrival rate is
Lambda.
no, the row.
Oh,
How much is your row? Say 0.2.
yeah. 0.2.
Just put there 0.2. And then service rate is 1. And then number of server is 2. And calculate. Now you the queue length in the system or in the queue. It's up to you. So in the system, so 0.2, 0.202, and then 1.12. That is the one that you input.
Okay. And
Lambda.
then
The delay also you input. 1 point.
the system.
Yeah. If you are using system, put the system. So 1 point.
Oh,
Now you change the arrival rate, now becomes 0.5. You calculate again. Now you get the delay. The delay is 0.5 now, 0.533, right?
um,
533.
it's good.
And then the delay is
6, 7, 8, 9.
Okay. Next, you increase, become how much? For example, 1. You calculate again, and then you get the result. You there.
It's the same. It's the same between the one and
Yeah.
the delay.
Okay. And then you increase 1.5. So 3.4. And
then 28. Okay, and then we make the graph.
yeah. Wait, before you make the graph, you need to also calculate the same row, the same mu, if the server is actually MM1. So if the server is MM1, how do you calculate that?
Using the MM1.
Yes. So each line will have, now the arrival rate is lambda over S. Right, so S is
Lambda.
2. So in this case, actually what you need to calculate is the lambda here. Lambda is equal to rho over S right now. Your rho is
Oh,
0.2
the S is 1.
divided by 2. Yes, enter. So you put it in, copy. Okay, so now you input this lambda 0.1, but the number of server is only 1 in that calculator.
This
One.
is only 1.
Yes, arrival rate is 0.1.
0.
Enter, calculate. There, you get 0.111 and 1.111.
0.8, 0.111, and 1.
Okay. Now you increase become 0.25. Okay, you just copy 0.33 and 1.33.
Oh, 1 and 2. Two and
3 and 4. Okay. Now, for the same row, so this is, now you can put that this is MMS and this is N times MM1, right?
This one.
This one is MMS. This is 2 times MM1 times 2. Multiplied by 2, right? Okay. And for the same row, now you can plot L and for the 2, to the MMS and MM1 times 2. For the same row, you can chart. Scatter. Scatter, not line. Yes,
Oh,
scatter plot. Yeah, that one. Okay. Now you add one more. Yeah, that's fine. Yeah. Okay. Now you add one more. In the same chart, you add one more from row and L again. So you go to select data. Okay. And then add. There, you put this is MM1 times 2. Series name. And then X is the row here in the bottom. E10, yeah. No, no. Yeah, anyway, that's
oh,
yeah.
this one.
Yes. And then the Y is the F10. Right. Okay, click OK. Now you can see. Maybe you should keep name. blue one so that you can see the legend. Go to select data again. So for the first one, you can give name, edit. That one is what? MMS, right? MM2. So MM2. Okay. Okay. So you just put okay. And then you okay, show the add chart element there in the yes. So add legend. Okay, up to you where you want to put it. There. So now you can see MMS. This is L, right? This at the bottom is row, and then on the vertical axis is L. So you can put the add element, add chart element. So you can put axis title. The primary is, what is that, row? Just type row. Okay, and then for the vertical axis, that is L. Very good. Okay, so now you do the same thing, okay, but for W. So you insert new scatter. So you select data, edit, right? That one is M. The X is the row, right? And then the Y is the W. W, not L. You already.
Oh, sorry.
Okay. Then click OK. Add. The second one. This is MM1 times 2. Okay, the X is again the row. And then the Y is the W for that.
Like I need to move this.
You need to move it.
Yeah.
Okay. Cancel it first. You just put anything first so that you can click.
Yeah, just do
You just click any cell there so that you can click OK. There.
Okay, and then
You select data and add.
and small and
The Y, W. Add M1 times 2. The X row. The Y is the W. Okay. Oh. Now you see. You put the legend again. That is the row. And that is W. give me conclusion. What is your conclusion? Which one?
So,
Oh,
okay. So, in terms of the length,
yes.
it's better for us to choose the MMS,
No.
but
L. Remember, L and W are painful, not benefit. Okay. Longer queue length is bad. Okay. Longer delay is bad. So less is better. Pain.
oh,
This is painful.
so for the in terms of the waiting line, the waiting line, we better choose MM1 multiplied
Right.
by 2.
Right.
But in terms of the
Delay.
waiting, the delay, the waiting time, it's better to choose the MMS.
MMS is better.
Yes.
Okay. So,
Sir, I have a question.
go.
So for example, if you're since for the uh queuing line, it's better to use MMS. For the waiting time, it's better to use MM1, right?
Uh,
So if you're a business, which one will you choose?
Depends on the situation that you want to use.
Oh, okay, okay. So
Okay. So, with among queue length and delay, which one is better for you?
queue line, I guess.
depends
Because
on the space I have.
Yeah, exactly. It depends on the condition, right? For example, if the person see the queue length is very long, okay, and then they said, "Oh, too long, I will go. I will not enter parking." Then you probably think the queue length is important. Yeah. But if the customer is very sensitive to the delay, then probably you will decide delay is the important performance that you want to set up. Depends on the situation, right? But the one that you just practice, yeah, you just did, okay? Very nice, isn't it? Right? So you just input the number, okay, and then you plot it. Now you start to get the conclusion, isn't it?
yes.
That is how you do research, you know. Very interesting, isn't it? Right. Without plotting, you will not understand, right? If you just see the formula, can you understand the situation? No, right? But once you plot and then you just compare, then you start to understand. Oh, uh, depends on queue length or queue wait delay that I want to set up. Okay, then the result will be different. Nice. Okay, so the next practice is taking very long. I will not do, but I will just show you. Okay. Okay, so I plot exactly the same thing with you, but I use program, so exactly the same result, right? Yeah. So I put it very small. This is for 2 and 10. Okay, server is 2. This is server is 10. It's exactly the same. You see, the blue and blue is exactly the same up. Yeah. So there is no change. Yeah, in terms of number of server increase. Okay. The same thing here for waiting time. Okay, whether the server is 2 or 10 is the same. Yeah. So the red one is this multiple line is always above the single line here for the delay, right? So clear? Now, for the same demand, the same service, okay? So this is the conclusion, right? Multiple line is better in terms of queue length. Okay? You see, of course, queue length is shorter. Okay? Single line will create very long queue line. Okay? terms of delay, okay, single line is actually better. Okay. So, but be careful, okay? So be careful that this model, okay, does not take into account of the walking distance. Okay? So up to certain time, certain number of server, for example, 10 number of server, actually the walking distance can be significant, right? Okay, so in that case, not necessarily the previous conclusion is true, right? So then we can start to check, okay? So in this practice, if you want, so anyway, I did it. So I try, okay, to accommodate walking distance by adding v-seconds to the service time per additional server from one. Yeah. So for example, two server, you need to add additional walking distance here. Okay. Now the question is single line actually still better than multiple line or not? So you can try this for different v-seconds. Yeah. And the service time computation is something like this. So the current service rate is 1, right? So that means one customer per minute. Okay, that means 60 seconds per customer, right? So suppose you have two server, you add additional, say, 2.5 seconds per customer, yeah, forward walking distance. So that will make the current service rate into 62 seconds per customer, right? So in that case, you put this 60 divided by 62.5, you get 0.96 customer per minute. Again, if you put 3 server with additional 2 seconds per customer, okay, you put that into become 65 seconds per customer, right? So that means the time now become 0.923077 customer per minute. Yeah, that is how you compute. Okay, using that computation, so you can see it here. Is it better or not? So in terms of queue length, okay, the multiple line is better, right? And then in terms of waiting time, in terms of waiting time, it's the same, yeah. So there are, depending on the row here, you can see now we have what is this, starting to have a conflict, crossing, yeah, between the two, right? So if the walking time is actually increased, you see here, so that there is a crossing again between these two lines here. And if the walking time is actually very big, okay, so it's not necessarily better. Yeah? So look, this is the conclusion. For the same demand and service and additional walking time, okay, multiple line is still better in terms of queue length, right? But in terms of waiting time, okay, when the walking distance is low, so single line is better. But when the walking distance is actually high, multiple line is actually better. Okay, and the crossing means the behavior will change as we increase the number of server and the demand. Okay, can you see that there is a crossing here? Again, there is a crossing here, and there is a crossing here. Right? Did you get it? Can you understand the meaning of this graph now?
Yes.
right? So the crossing mean this one is the red and the blue line is crossed here, right? Okay, intersect. Okay, the same thing here. The red and blue is intersect here. Same. So that means look below this crossing point. Okay, the red is actually higher than the blue. After this crossing point, the blue is actually higher than the red, right? So up to certain value of the row, okay, the multiple line will become delay become lower, much lower than the single line. Okay, so the walking distance matter in this case. Yeah. Is it clear? So again, if you don't calculate the walking distance, the one that you just make is correct. Okay? But if you consider the walking distance, so then you need to deal with it. Yeah? There are certain crossing for that. So the important things you need to remember is MMS is dealing with single line and parallel server. Okay, and then S of the multiple MM1 is the multi-line queue. Okay, this is the one that you need to remember that. Okay, up to here, is there any question? Clear, yeah? Okay, so the next slide is the idea of creating an optimization. Okay, so to create an optimization, we need costs. Okay, so I will you go to the next slide. Okay, queuing optimization. So this is a very basic, because this is OR, so OR is dealing with optimization, right? So okay, we need to discuss about total cost and economic analysis of the queue. Okay, and we discuss about this queuing optimization. Okay, so I hope by the end of this slide, you will be able to find the cost-effective queuing channel. What is that? We want to know the number of server that is the optimum, yeah, cost-effective in this case. And then you can also find the cost-effective service rate. Yeah? And of course, you can model your own queuing decision model. Yeah? So here it is. We have system average cost equal to the service cost plus the waiting cost. Okay, what is service cost? Service cost is the expenses of owning or renting, operating, okay, or maintaining the service facility. That means the cost of capital, for example, the equipment, the land, the building, depreciation costs, including operating costs, for example, rental fees, the labor, the material, the repair, maintenance, and so on, including the insurance and the taxes. Okay, so the service cost in here is directly proportional to the level of service, right? Meaning you add the server, you train the server, right? Or you add more rooms, more seats, and so on. So by adding server, okay, you increase the service cost. By improving the giving training to the service, the server to improve the service time, again, it will cost you higher. That is called service cost. Okay, what is waiting cost? Waiting costs occur when the customers stay in the queuing system. That means the cost of production loss, for example, when the employees wait for the tools or machine waiting for the maintenance crew. So there is a example again is the opportunity loss for the present and future profit because of customer dissatisfaction. Okay, so they will go to your competitor instead of going to you. So another example is the aircraft waiting for the runway, okay, or the air pollution, okay, that will create the fuel and environmental costs. Okay, look at this. The waiting cost will decrease, okay, when the level of service increase. So, wow, you see, the service cost will increase if the level of service increase, okay? But the waiting cost will decrease when the level of service increase. So we can add them together, right? Because they are in conflict. So you can add them together, then you can have what is called total cost. So the optimization is basically the cost of waiting, okay, and the service cost. So then you can say, look, the cost of waiting is, I can put as length, yeah, queue length, or the waiting cost, right? And then the service cost depend on the number of server, right? So then you want to minimize this total cost, okay, in order to find the service, the number of server. Okay, so queuing optimization is basically just that. Okay, so this is an example, yeah. So direct observation of 2,400 customers that arrived during 200 hours, showing that their total waiting time in line was 640 hours, while the total service time given to them was 160 hours. Waiting cost estimated $50 per each hour of customer to stay in the system, and service cost is $8 per hour. So now find the average system cost per hour based on this 200 hours observation. So if you look at this, okay, the system cost during this observation is what? The service cost, okay, plus the number of hours, right? And then the customer waiting cost multiplied by the customer average time in the system. So you can calculate that as 8 times 200 plus 50 times 800. So you get, say, 41,600 in this case, right? And then you divide again by 200. Then this is the system average cost per hour. Is it clear or not? How you calculate the system average cost per hour here? Okay, this is just an example of 1 point. Okay, of course, in reality, you don't calculate 1 point, you calculate many points. Okay, when you calculate many points of the total cost here, the system, okay, you add this, you can see here the service cost, okay, is equal to the CS. What is this? This is the unit service cost multiply the number of server, right? So number of server is number of channel, yeah. And then when you increase the number of server, of course, the waiting cost decrease not exponentially, non-linearly, yeah? Non-linearly decrease. So you add the two of them, you get this total cost, right? So you want to minimize the total cost. This is not exactly in the crossing point here, okay, but close to this crossing point between the two lines. Yeah? So we want to minimize this. Okay, so Given the multi-server system, MMS, okay, so you know the lambda, mu, and then CW and CS. So this is all given. So then you increase, yeah? S is 1, 2, 3, 4, and so on. Then you calculate TC. Okay? And then now you want to minimize the TC. Okay? So look at this. The change in S will affect both service cost and the value of L. L is the queue length here, right? So look, you don't need to consider the value of TC for the S which does not satisfy this equation, yeah? Because this is above what is this equation about? The utilization factor is larger than 1. You don't need to consider. Okay, the meaning of this. Okay, so queuing optimization is done only when utilization factor is less than 1. Right? So I already have the computed calculator, so you just input, very easy. Right? So you can just calculate. So you can try. Okay. Say you have, oh, lambda now very big, 5, and then mu is 1. Okay, so I use 2 peso here. You can put any value. Say I put 50 pesos here is about $1 per hour. That's an opportunity cost of losing customer. You can put any number. Okay, and then what is the economical number of channel? Okay, and I can put into Excel also if you want. Oh, and if you plot it, you can get how many servers. Okay. And try this and compare this with the queuing rule of thumb. Okay. This is MMS, right? So try to compare with the queuing rule of thumb. How many servers do you actually need it for this row and lambda and mu? The calculator is there, so you just input the number. So how many servers? So what do you think? Is there any problem? No, you just input this value, you will get the sum load server already. You don't need to plot.
Sir, for the rule of thumb, the service duration is
Service duration. Oh, if you have lambda over mu, what is lambda here? Lambda
Arrival rate.
arrival rate is actually equal to n over t, isn't it?
Hmm.
So now it's up to you to put what is your t. So for example, if you put t is equal 1, then n is equal to lambda. Right? So economically,
For the rule of yeah.
sorry. What?
Okay. No, for the rule of thumb is the answer like S must be bigger than or equal to 6.
6 must be larger than 6. So, and then if you use this uh, optimization, MMS optimization, how much?
7.
7. Okay. So larger than 6 is okay, right? So economically 7. Okay. Rule of thumb will only give you the minimum. Okay. The worst case, actually. The rule of thumb will give you the worst case. Okay. The optimum is 7. But if you put 8, it's not optimum in terms of the cost. Okay? But if you 6 is minimum, if you put 5, the queue will go to infinity. Clear? Okay? The rule of thumb will give you the very hard minimum because the rule of thumb is actually based on utilization factor. Clear, yeah? So the optimum is 7 in this case, yeah? And that optimum value depends on the cost that you put, yeah? So, okay, up to here, is there any question? What do you think? Can you put this into a practical use? Right? Probably your question is, how do I get the C, W, and CS?
We can assume that, right? For example,
Yes,
if I want to compare models, I can just assume the same number for both of them.
yes. You can also, of course, you can assume something. Okay. This one I did not put the same number, right? So the server cost is actually clear. That's easy to compute, server cost, right? Because that depending on the wages, okay, your investment. So probably what the difficulty is actually to get the opportunity cost. So that one usually the marketer will calculate. Yeah? The marketer in the business will calculate how much is one customer worth for a lifetime. That is how you calculate that opportunity loss. Okay. So the loyal customer, how much is the one customer worth for a lifetime? That is the one that you can calculate as opportunity cost. Right? Meaning, say, one customer will, on average, how much they buy. And then in a lifetime, okay, for example, oh, that customer will buy every month, for example, okay, for how many years? That is the worth of the customer. Clear, yeah? And then the wages is also easy, right? Because say how much is their salary per month, and then you just divide the number of hours, you get the same rupiah per hour. You see? Okay, so with that, you can have here. So look, I give you the formula a while ago, does not mean that you will use that formula, right? That formula a while ago, I used L, right? For the, well, the formula a while ago, I use L, isn't it? This one, CW times L, correct? But you said, look, I don't care about the number of queue length, I care about the delay. Then you can use delay. Okay, but be careful when you use delay here. What you will do? CW will change the units. Okay, so the important here is total cost must be in the same unit as this one. Okay, so you need to change so that the unit will be all the same. Yeah. Of course, total cost is cost, right? That means should be in monetary term, yeah, either in dollar or in rupiah, yeah, in pesos and so on. So that is the most important part there. Okay, so you see here is the level of service, yeah. LOS is the level of service, yeah. So the level of service will increase, okay, if this variable values increase, okay? And then the level of service will increase if this variable values decrease. Okay? So when you look at these two things, you can see the conflict. Okay? So if you want to find optimization, this is the principle. Yeah? So find the conflicting values. Okay? Very important technique to do optimization, not just for the queuing, okay, is find the conflicting measurement of the performance, and then when you add them together, then you can find the optimization value. Is it clear or not? Check. In the future, you will do optimization in different things, right? Not just queuing, right? Okay. Say, at that point, your goal is, oh, I want to optimize this. How do I optimize? Okay. So I said there are many ways to optimize. Okay. So in principle is to find the conflicting measurement of performance, and then which variable will increase and the other one will decrease. And then you add them together, okay, then you will get the optimization. Is it clear or not? I think last year, one of your senior doing, for example, the performance of airport, for example. Yeah? So, or the other one is using for parking system. Okay? So that the variable that they use is totally different from here. So in that case, I said, look, if you want to do it, what you need to do is to find the conflicting measurement of performance. Okay. For example, the number of empty spaces. This is another example. We can also do optimum service rate. Yeah? So instead of C S, I can use C mu. Right? Why not? Right? Because this is conflicting. Right? The L and mu is conflicting, so I can just put them together. Okay. The most important is, look, this unit is not the same as earlier. Yeah? So this is now cost per unit increase in service rate per unit of time. Okay. So using that, you can calculate, say, if I use this formula, okay, for MM1, of course, this is clear. L is already using this formula, right? Okay, and then you calculate, say you want to do, because the service rate is continuous, so you can take the first derivative. So, right? So if you get the first derivative, you can get the mu is equal to this formula. Okay, so in this case, what the service rate is now depend on the arrival rate and the ratio between the costs. Okay, and the optimal service rate is always greater than the arrival rate. Okay, so okay, based on this formula, then suddenly you can get a new formula here that you can derive on your own. Is it clear or not? So the same thing, yeah. If you say later we will discuss MM1N. What is this? N is the system capacity. Yeah? So you have a capacity instead of infinite, right? So you have a capacity. So now you can put a TC. Now depend on N, for example, and depend on the probability of the system. Okay. So again, this is conflicting. Look, using this technique, you can have a different optimization. Okay. So another model. So using MMS, okay, you want to find the number of server so that, for example, the expecting waiting time is smaller than certain threshold. Okay. And then say the percentage server idle time is below certain threshold. Okay, so in that case, you can use different model of optimization. Okay. Now, again, if the two condition in this case is not satisfied simultaneously, then you can relax one or the two threshold. This is just to give you ideas, okay? The standard optimization is this one, right? This is the standard, okay? But I'm trying to generalize this, okay? So that you will see, look, this is not the only one, right? So you can optimize anything, okay? So I give you the principle to optimize anything, right? Find the conflicting measurement of performance. One is increased, the other one is decreased. Okay, with that, now I give you example of that. Okay, these are the example of different conflicting measurement. So, the point is actually you want to get the number of server or the improvement of service time, right? And the unit cost is based on certain subjective evaluation of your operating characteristic. Yeah? So from here you can see, okay, basically optimization is considered both view. Okay, one is the customer point of view, the other one is the demand and supply. Yeah, the supply is from the company of point of view. You want to find both sides. Okay. So from here you can see this is the optimization. Okay, so tell me what did you learn today as a feedback? Can you summarize?
So we learn about MM1, then MMS, then we learn how to
Can you distinguish M1 times N?
distinguish between MM1 and MMS.
Okay. And then
So MM1 is single queue multi-server.
MM1 is, no, MM1 is one server. One server, one line.
Oh yeah, MM1 is one server, one line. MMS is one queue, multiple server.
One queue, multiple server, correct. Right. So if you have multiple queue, multiple server, that is
MM1
M1 multiplied by,
S.
correct, very good. Yeah, that is,
Yeah. The name is tricky.
the name is tricky. The name is tricky.
Yeah, then we learn about how useful using graph is, since we can
Yes,
see is it better to use MM1 or MMS.
correct.
Then we learn about optimization,
Yes,
calculating costs. So like the total cost, the total system cost equals to wait, cost of waiting multiplied by L, or you can change it with anything, plus
yes.
cost of serve
So,
S multiplied by the number of server.
right. And again, this is, S is one of example. Okay. So not necessarily S, yeah. I show you a while ago. Instead of S, I can change to mu, right?
Yeah.
So the principle is important here, right? So find the conflicting situation. Okay. So look at this. If you have a conflicting situation, then you can optimize. If you cannot find the conflicting situation, then you cannot optimize. So conflict is actually very good for you, because with that, you can find the optimization. So optimization is basically a trade-off, okay, between one situation and the other. So you want to find a compromise between the two, conflict. Okay, that is the principle of OR here. Once you understand this, you can optimize anything, isn't it? Okay. Okay, so let's stop here and then continue next hour. Yeah. Let's continue. Okay. Uh, we have the next case, number 7. So, okay. You can open the next slide. It is the queue with limits. Yeah? Queue with limit and bulking. Okay. So I just search in. Okay, I just search in Google. So and there's a paper about it, 1963. Yeah, it's quite old. So you can, yeah, I can get that paper. So I can download that from the journal article. So it's basically bulking means refusing to join the queue. Okay, reneging means leaving the queue after entering. So there's some paper about this a long time ago, 1960. And if, basically, if you look at the computation, okay, this is just the usual formula for balance probability, and this is how they derive the formula to get the formula that we are using in this slide. Okay, so you can search by yourself if you want to know how can I get that formula and so on. Okay, so let's go to the slide. Okay, so the slide is this one. ready. Okay, so we discuss next case. Okay, it is again the detail. We have random arrival, random service time, right? So M here means random, Markovian, with Poisson distribution arrival and then exponential service time. The number of server is S, yeah, discrete, and then N here represent the limit of the capacity. So waiting room, this is the waiting, N is the number of waiting room capacity that will include the number of servers. Okay, so again, this is multi-channel with limiting capacity. Okay, so this is actually more realistic. Yeah, so when we do modeling, okay, we start with very general and with a lot of assumption, right? And then one by one we remove those assumptions. Okay, so this is in here. One of the assumptions that we remove is that the capacity is infinite. Okay? In this case, we put capacity is not infinite but finite. Yeah? Finite space capacity. So be careful here. When we say capacity, here is actually maximum possible queue length plus the number of servers. Okay. Otherwise, you think that capacity is the queue length, but in this formula is not. Okay, the formula is the maximum of the queue length, okay, LQ in this case, plus the SS is the number of servers. Okay. So if what will happen with this, what is the consequence of this? So if N is equal to S, what will happen if N is equal to S? If N is equal to S, then the maximum LQ is 0, right? Okay, so if the N is equal to S, this is S equal maximum LQ plus S, that means maximum LQ is 0. Okay, so what that mean the maximum LQ is 0? LQ is the queue length, right? So if the maximum queue length is 0, that means it will not receive any customer. Okay, that only one customer receive. Okay, and if the customer is being served, this is LQ and not L. So if the customer is being served, then new customer arrive, immediately working. Okay, immediately go. So in fact, this is the formula that actually proposed originally by Erlang in 1917. Right? Why? Because this is his model is based on telephone. When you have a telephone, okay, when someone call you, okay, and someone else want to call you, cannot, right? Okay. At least the older phone. Yeah, probably the new phone can do, but the older phone cannot do. Okay, so when someone call, when you are on call, okay, and then someone else call you, okay, automatically rejected. So that's the meaning of this. If S equal to maximum LQ plus S, yeah? If N equal to S. Okay, so if the customer arrive and the system reach the capacity, and then that customer will be rejected. That's the meaning of this maximum capacity. Yeah, so it either turn away or denied of service. Okay. So now the arriving customer will see the system in the capacity state of N are lost. Okay? So they will not come. So before we continue, tell me what queuing system has no limit of capacity? So if you have going to doctor, for example, yeah, you need to queue, right, for the service, and there is a room to wait, right, and is that room reach the capacity? Will you still stay or not? That's the question. So if the doctor's room reach the capacity but can go out, if the patient or the customer of that doctor, the patient is actually arrive and then still exit outside the room, okay, then actually it has no limit of capacity. Do you understand the meaning? Limit of capacity mean if the doctor's room is already full when you arrive, then you don't join the queue anymore. Okay, that's the meaning of limit. So if they allow you to wait outside of that room, then there is no limit, right? Because it can go to infinity. Theoretically, at least theoretically. Okay, so I hope you understand the meaning of capacity here. Capacity means when you enter, okay, and you see that when you join the queue and you see that actually it's already full, okay, then you don't join the queue. That's the meaning. Okay, so the formula that we discussed in this slide is based on that assumption. Okay, again, when we model, we need to know the meaning of assumption. That is the most important part. Yeah. So what is this? Here, bulking. Yeah? Bulking is PN. So probability of denial of service is the probability that an arriving customer find the waiting room full and then will be turned away. Yeah? So this is N. This is the N customer. So when N equal to N, N capital here is the capacity, then it is actually probability of bulking. Okay. Okay. So the others is the same, yeah, meaning. Okay. So the formula is a little bit different because of course we use MM1N here. This is only one server. Okay, so because this is only one, so you use rho is lambda per mu of less than 1, and you can calculate all of this using this formula. Okay. Okay, so all the others are the same except this two assumption. Yeah, there is no reneging on joking, but there is bulking, and then I think the waiting area is limited to N. Okay, this is the assumption of MMSN. Okay, a while ago the formula is for MMS1. Now I improve it to MMSN. So these are the formula. Again, you use P, which is very complicated formula using factorial and so on, similar to MMS. Okay, and these are the other formula. Okay. Okay, so I think I also make the calculator there in my website about this, so you can use. Oh yeah, I have it. So you can also use this. Huh? Can you try using the same lambda and mu a while ago? Okay. What happened if you set certain capacity. What happens if you set certain capacity? And what happens if the capacity is equal to the number of servers? So can you try this? So if the arrival rate is 5, service rate is 7, 2 server, and then you have a capacity of 5 customers. So you want to share your screen or?
Oh yeah, I can share my screen.
Yeah, okay. So yeah, this is 2, right? So you get the queue length in the system 0.8 all time. And remember, this queue length and delay have unit. Okay, the unit is the same as you need to define your unit here. Yeah, arrival rate and service rate unit. Okay, that one is the one that determines the unit of queue length and the delay. Okay, so next question. How to improve the queue length capacity? Suppose you have limited area. Is there any way to improve queue length capacity? Any idea? The area is still the same. You often see this actually. Say you are in the airport, right? And then the queue length is so long, what they do? What they do in the airport?
Oh, so it's not long backwards like this.
Yeah. So in the airport, what they do is to create a meander, right? So something like this. Okay. So instead of one line, okay. So this is basically the idea is to convert 1D. Yeah? One line is one dimension, right? So on the top view, okay, is one line is one dimension. So you convert it into 2D. Yeah? So 2 dimensions. So you use the whole area, okay, from the top view. You put the whole area as the queue length. So in that case, yes, you will have a longer queue length. And because of this meander system, so you probably don't, sometimes you don't see, yeah? Because of the wall, you don't actually see the queue length. Yeah? So you only see, the arriving customer only see the part of the queue that is in front, so they don't know the actual length. Okay. So in that case, you can avoid bulking, okay, using perception. Okay. Okay, so now can you compare, okay, for any the same arrival rate, the same service rate, okay, and then the same number of server, okay? Can you compare MMS and then MMSN. Can you compare? Yeah. Take note or I put in the Excel like a while ago. Okay. Which one is better actually? You can set two. Yeah? One is, okay, Livy, can you put n equal to s? Joy, can you put n equal to 2s? Which one is better in terms of queue length and waiting time? And then how much reduction? And then you tell me what does it mean for the long-term relationship with the customer. Practice research. Anyway, you have the calculator, so all you need to do is just input the same number, okay, and then comparing two calculators. You can share your screen. You know what to do, right? Just input two numbers, or three with n. N is up to you. So,
I'll share my screen.
yeah, go. So that is MMS, and then MMN. Okay, so in terms of L, which is better?
This one. The less the better, right? The
The
smaller the
less the
better, right?
better. The smaller the better. Yeah, the smaller the better. So in that case, the MMSN is actually better. Yeah? Both sides. Okay. So in terms of performance, okay, why this is better? What is the meaning of n equal to s?
Meaning that the capacity, the number of server is double the number of capacity.
No, number of capacity is double the number of server. That means only one customer waiting per server, only one customer waiting.
Hmm.
Okay. Remember, n is equal to s plus LQ, maximum LQ. Yeah. N in here is the capacity, right? Capacity is the same of the number of customer, the number of length, queue length, plus the number of server. Okay, so when you put 2s in here, that means the queue length itself is the same as s.
Hmm.
Okay, okay. Livy, in your case, n equal to s. What happened?
Oh wait.
Joy, can you put n equal to s with your number? What happened? Because your row per mu is not.
N equal to, Okay.
not the same as living.
Zero to zero, one, zero, nine. Oh,
It's actually better, like smaller,
Why?
because now there's no one waiting.
Yeah, because there is no waiting. No one waiting because it's bulking, right? So, look, the performance seems look good
Mhm.
in the MMS, yeah? But in terms of cost, it's actually much higher. So be careful with that. Okay. The way you measure the performance, you should understand the meaning. Okay. Because MMSN, that means there is bulking, meaning you kick out the customer. When then you check, oh, is it performance is better or not? Yes, of course, you kick out the customer. So there is no one waiting.
Sir, can I share my
Yeah,
screen?
yeah, okay, go.
Here, for my case,
In your case, what is your lambda? What is your mu?
I use lambda as, let me write it.
Uh-uh.
Lambda 0.1
Okay.
mu equal to 1.
The mu is 1, very small. And then n, what is your s? What is your s and what is your n?
My S, I think I make it 1, 1. Oh,
1,
no. The N is 2. N is 2. And
2.
the
So then the s is 2.
1.
Ah, this is Toko. Okay. So can you try also if the s is actually
2.
same as n?
Okay. Wait. Wait. Mm. The S same as N.
So if the s, if the n is actually much bigger than s, okay, in this case 2 times, right? So can have different performance. Okay, which one is improved or not? So you can test. Yeah. In case of Joy a while ago, she said both, yeah, L and W is actually better in MMSN, right? The one with bulking. Now, can you compare also MM1N, MM11, MMSS? Practice 3. Can you go to the next two?
It MM1N.
M1N. Okay, so I will show it. You also compare. Okay. And
Oh, okay. MM11 and MMSS.
yeah.
Oh my God. They all sound so similar. But I'm kind of confused sometimes.
Yeah, but I hope you understand the meaning, right? This one, right? This means you have only one server, okay, with the capacity of n. Yeah? This one is only one server with only one capacity. Okay, so meaning that each customer arrive is rejected. Okay, if the server is busy, yeah. If the so it's meaning can only receive one customer. This one. Yeah. In here it has S server, and then it can receive up to S customer being served. So after that, the customer will be rejected. Livi, you want to share your screen?
Okay. Yeah.
Okay. So if f is equal to n, what is this of n is equal, exactly equal, 0.1, 0.1,
Yeah.
and then this one is smaller. W is smaller for MMSN.
Mhm.
So in general, MMSN supposed to be smaller, right? Because especially when S equal to N. Why? Because it's rejecting the customer, right? I think logically. But again, you be careful, okay? When you see the performance is better, you will be attracted to it. But you should understand the meaning, okay? I said, if you are attracted to this MMSN, okay, and N equal to S, that means you are actually rejecting customer. So in terms of cost, and I mean in terms of opportunity cost, it can be very much higher. Okay, in that case, how do you make the performance evaluation or the total cost in that case? The optimization is not the same as before, right? In that case, you should include the probability that the customer is being rejected, isn't it? Right? Otherwise, it's unfair, right? The system will not be the same as a MMS. So, so I give you the example here. Okay. So this is all the same earlier, right? But now you add, yeah? You add additional cost. Okay. That the customer is actually refuse of service. Can I? This one. Can you see?
Yes.
You add this term in the last, okay, part that represent, look, there is a denial of service that you need to include. Yeah? Otherwise, it's unfair. Yeah. Okay, so the optimization procedure, okay, you should include all the possible problem that we have. That is the point here. Okay. Okay. Next one before this is the important part here. Okay. So if we have MM1N, right? That means you have only single server with limited waiting room. Limited waiting room. What is the waiting room capacity? N. Okay. What is the meaning of MM11? Okay. That means a single server with no waiting room. That means the customer cannot be served and then will leave the system. Okay. So if it doesn't mean there is no customer can enter the system. Okay. There is only one customer can enter the system and immediately being served. But when that customer is being served, no other customer will be able to enter the system. Yeah. Again, this is similar to a phone, yeah, the old phone. So when you are on call, right, someone else calling you will be rejected. Okay, and because they are starting from the phone, so this is when you have S customer, S server, okay, and then N is equal to S in here. So this is sometimes called Erlang loss system. Okay, that means the customer arrive when the server or PC are not allowed to enter the system. Yeah, this is more general than this one. The difference is only S instead of 1. Okay, is this clear or not? What's the difference between MM1N, okay, MNSN with MMS? Can you see the difference or not? Okay, so without knowing the difference, then you get confused, right? First time, oh, why so many things like that? It's look like the same name, right? All with MM something, yeah. So basically, you need to understand the Kendall notation. Okay. Okay. So, is there any question about this MMSN?
Sir, can you repeat the difference between MMSS and MM11?
Which one? MM
11 and MMSS.
MM11 and then
MMSS.
SS. Oh, what's the difference? Oh, what's the difference? It's the same, yeah. So when we said 1 this means one server, right? And then one waiting line. One. So this is actually the same. S is general. 2 can be 3, right? So this is more general than this one.
So basically, it's the same.
This is the same. Okay.
Okay.
Only different is the number of server, right? But the meaning is this. Yeah. If you have MMSS, yeah, and then S is equal 1, yeah, in this case, right? So what is the meaning? If the number of server is equal to the number of capacity, okay, that means when all server are busy, okay, serving customer, and then new arriving customer will be rejected. Okay. Why is
Okay.
so? Why, yes.
What about MM1S?
M1.
1S.
What is S? What is S first?
The server.
Yeah, but the server is already said 1.
Oh, so it will also be MM11 then.
Right,
Oh, okay.
right.
Oh, but what about okay, so S multiplied by MM1, right? So multiple server and multiple queue.
Yes.
And then,
M1 and then multiply by S. That is multiple server and multiple queue. That one.
if MM1 N multiplied by many server, is it possible?
MM1 and that means MM1N multiplied by many server possible.
Oh, okay.
Possible. That means you have many queuing, but each will have limited capacity. Possible. So you want to have, okay, let me put in the note here. I will create a new here, right? This is what you mean. So you will have M1, N, right? And then you multiply by
S.
up to K.
Okay.
Okay, multiply by K, right? So basically, this means you will have for each you will have one server with limited capacity of N, right? And then you have a number of K number of this multiple line. It's possible.
Okay. Oh, the assumption is there is no choking. Yeah. That's why we
There is
count
no
it per
choking.
line.
Yes.
Okay.
Okay.
Will we learn about something with that allows
Choking.
choking?
No, you need to. I don't know. Is there any formula for that, or maybe there is some paper on that? I'm not aware. So, or you want to do it? I don't know. As your just paper. Okay. So there must be someone already doing. Okay. But that's basically on the research part already. Okay. Not in the textbook. So again, there are so many possibilities in queuing, right, that each have different special scenario. But at least the one that we discuss here are quite general. Okay, so the next one that I want to show you, okay, this is finished, yeah. I will close this, yeah. The next one is actually number 9. MSNN. This is so that to make you more confused. So in service queue, okay, this is used in industrial engineering. So you are part of industrial engineering student anyway, right? Okay, what is this? Okay, now a while ago, okay, all the skewing that we discussed, we have one assumption, crucial assumption. What is the assumption? Population is infinite, right? So in here, we remove that assumption, okay, that there is a limit in the population. And that limit is exactly the same as the n. Okay, that. So adding limit capacity and then limit the population. So what is this happening? Yeah? So this is happening because we have a machine. Yeah? So a broken machine need to be repaired, right? So while in service, the broken machine cannot generate new arrival for service. Right? If the machine is, say you have limited number of machines, you have 5 machines, okay? And then the service is to maintain this machine. So the population, in this case, is limited, which is the number of machines that you have. So that's why this is called machine service model. Okay, so in this case, the number of population, which is the number of machine, is finite. So what is the server? The server is the repairman. Right? Okay, and then the total number of machine is n. Okay, but the capacity is also the same as the number of machine, isn't it? Okay, because there is no new machine will enter the system because the population is n. Okay, and this is a crucial assumption. The number of server must be less than the number of machine. Yeah? So using that, okay, the formula is now the Kendall notation. You get 5. This is the full Kendall notation. Okay, 5. What is this? Actually, Kendall notation is 6. Yeah? 6 A, B, C, D, E. Yeah? And here I could put only 5 first. Yeah? So what is C in here is the capacity a while ago. Yeah? Okay, the capacity. And then D in here is the domain or the population. Okay. So basically, I'm just trying to keep you understanding. The first thing is MM1, MMS is only the first 3, right? Okay. A while ago, I add one more, number 4, right? C in here is N a while ago. Okay. Now we have 5. Is this confusing or not? Somewhat, yeah.
Bit confusing.
Still confusing. You just know the A, what is A in here? Arrival. Yeah. B in here is the service. Right? The third one in here is the number of server. Okay. The fourth one is always the capacity. Okay. And the fifth one is the population. Okay. The sixth, the last letter is the queuing discipline, FIFO. Okay, so that's the full Kendall notation. So now we have 5, and this N is always the same as the population, and the capacity is always the same, yeah, N. Actually, what they want to limit is the population, right? But if the population is limited, then capacity is automatically limited, exactly the same as that, isn't it? Okay. So this is the formula. I'm not sure if I have this. Oh, I have. I created also. Okay. I forgot because this is like more than 10 years ago I make it. So
Oh.
2011. Yeah, a long time ago. Okay, so I have. So in the last one, I don't have the priority queue. I did not make it. For this one, I make. Yay! At least you can use this. Okay. Okay, so you can just input, and then you can compare. Okay. See, N in here is the number of machine, yeah, that you have. Okay, so if you have number of capacity is the same as population, so MM, right? So that's why I put in the same number here, and then the number of server. Okay, so here I give exactly the same as previous examples, so 60 and 75, and then number of server is 1, and then so that you can compare, yeah? So that you can compare the delay and the queue length. Okay. Wow, the queue length is actually very big. Yeah. The delay is much smaller, but the queue length is much bigger. Yeah. So, yeah. So how to improve the queue length capacity? We already said about a while ago. So with the meander system, yeah. Okay, so at least I hope you understand the meaning only, so that you will not confuse. What is the meaning of NMSN? Okay, up to here, and then with the fifth number here, so that you will not get confused with that. The rest is just calculator, so you just input the number then finish. Okay. Okay, give me your comment, no problem.
Yeah, yeah, it's okay because we have your calculator.
The
So I
calculator.
just need to understand how to use the calculator. Then
Yeah, you only need to
improve.
understand the meaning so that you know which calculator you will use, right?
Yeah, true. Then we just like, okay, we need to put this number here and there. Then just
Yes.
calculate, and we have
Yeah, just
everything.
calculate, you get everything. Okay. So next time, if I have time, I will improve the calculator so that I'm planning for a long time. Actually, before I have it, but uh, the I mean, the program's still there, but the drawing is not there anymore because the library that I use is no longer exists. So then it doesn't work. So I remove it. Next time I will improve it so that I can get the probability, something like this. The probability
Oh,
of PN. The PN is the problem. I mean the drawing one.
oh, sir, my project is about queuing, right? So can I use your calculator?
Of course.
Okay.
Not only you use this calculator, all over the world people are using the same.
Yeah, that's why I kept on thinking, okay, students must be so grateful for your calculators. In exam, they just type it in then.
In fact, the professor in MIT just contacted me a few months ago. Okay, they just said, "Oh, I will use your calculator in my class." MIT. Okay, so anyway, so just joke, but the contact is true. Anyway, uh, I'm trying to contribute my work to the world. Okay, so this is just free things. With that, a lot of people coming, and I'm selling my calculator also. In terms of Excel, so it's the same thing. Okay, so at least you know how to use the system and what's the meaning. Okay, next, let's go to the, this is important, self-service. Self-service. Okay, we have 10 minutes. I think I can finish this. Of course, this one I have the calculator. I know this because I love this very much. Okay, self-service system. Can you see my slide? Yeah, self-service model. Yeah. So what is the meaning of self-service? Remember I explained last time. Self-service mean uh, basically similar to online system. Okay. So the self-service is just three. Okay, A, B, K, and the K is infinite. The number of server is infinite. Okay, so here it is. So infinite. Okay, so the number of server is unlimited. Why? Because this is all parallel. Yeah? Okay, the customer is the server. Okay, so if you let the customer become the server, it's self-service system. Yeah? So nowadays is if you let the customer to do it online, okay, then there is no queue, right? Well, there is. That is called self-service system, yeah. And but be careful, okay? This is again, these are not self-service. What they call self-service here, it seems like the customer is the server, okay? But this is not. Be careful, yeah. So the self-service gas station, yes, customer is the one who fill up the gas, but the actual server in that case is the gas pump, right? 24-hour banking, ATM machine is the server, yeah. So there is a queue. It's not self-service in this infinity, yeah. So the same thing with the self-service restaurant. So this name is misleading, okay. Basically, this is not self-service because the table of the food are the server. Yeah? The length of the table is the server. Okay, so be very careful. Last time I explained about this examples. Okay, so I will not repeat myself. Oh, do you want to give other real self-service model? Say you do an online shop, right? The customer is the one who fill up, okay, the order online, right? So in that case, the queuing is MMS, yeah, for the ordering system, okay? And look at the performance here. Wow, super simple, you see? Yeah, the probability of empty system is basically E exponent to the minus rho. Wow, yeah. And then LQ, what is LQ? Of course, 0, right? Okay, LQ is 0 and L is equal to rho. Hey, be careful, this is the exam problems. Yeah? I give you a highlighter, yeah? So these are the one that you should know. So I will say, okay, a system with the average system length, okay, equal to lambda per mu. What is that? Okay. Of course, you know that this is MM infinity, yeah, self-service system. Okay. Again, because no queue, right? The waiting, the delay is also 0. Yeah. But the delay in the system, what? Of course, 1 over mu. What is this 1 over mu? This is the service time. Yeah. 1 over mu is the service time. Average service time, right? Okay. So Pn, okay, is just P0 multiplied by the same number here. This is the P0. E exponent minus rho is the P0. Yeah. So the others are the same thing. Okay. Right. So again, I have the calculator with only 2 numbers here as the input. Very easy. Okay. So here it is. This is the most important part of this slide. Okay. MM infinity can be approximated by MMS. Okay. So for example, when your S here, the number of server very high, 100. Okay. You will get almost the same number, the same value between MMS and MM infinity. Okay, but if you compute, of course, you don't use MMS to compute MM infinity, right? Why? Because the formula is really very simple, isn't it? You can see the formula is rather simple, yeah? So now, this is the most important part in this slide, okay? The MOE, the performance of the MM infinity, show the minimum boundary of the queue length and the delay, okay? That means MN infinity is the most efficient system, the most efficient queuing system. Okay. Okay, that's it. Okay, so next meeting we continue with the priority queue, and then we go to the next topic. Yeah? Just 3 minutes. Okay, now you have 3 minutes. You can discuss anything that you want. You're supposed to present your group project, your project. Are you going to present or?
You want me to present? It will be quick.
Okay, go.
Okay, it's a quick PPT because just like updates.
Yeah,
And
okay.
and it's about the topic today, so
Okay,
same
go.
thing.
Yeah, I think it's much.
Okay, wait. Oh no. I actually have to use my other pad because I will need to write. Okay, but anyways. Do you have enough time, sir? Is it okay if we go over a bit?
Yeah, no problem. The next class is half hour after this.
Okay.
Hoki mean lucky.
So actually it took a lot of time looking at similar studies about this.
Mm-hmm.
So I will focus mostly on the analysis and application of queuing theory in hockey. So I will try to improve their overall performance and minimize their costs
Okay.
because that's the whole point, right?
Right, right, right.
Okay, so next, okay, is the present scenario better? Currently, they are working with the MM1 model. So they have multiple server and multiple queue.
Okay. MM.
So
Yeah.
one of the first step I aim to do is actually to find the optimal number of person. Wait, sorry, wrong slide. Okay, find the okay this one, yeah. So
Mm.
one of the first models I want to develop is find the optimal number of servers that need to be open to fit the demand.
Okay.
So like a break-even point for the server for them to if they don't want to change their system that much, they can use
Mhm.
this one.
Mhm.
And another thing is from taking a look at a lot of papers, actually some supermarkets are more cost efficient and everything waiting efficient everything by having an MMS system. So I will try to also simulate to also check whether hockey is also the same with other supermarkets because a lot of supermarkets actually have like a better result with this whole system.
Yes, in terms of queuing time, the delay is better, right? Supposed to.
Yeah, that's why. And also by counting the total cost. Okay, wait. So assuming that the arrivals follow a Poisson probability
Mm-hmm.
at an average rate of like lambda customers per unit of time, then the queue discipline is first come first serve.
Mm-hmm.
Uh, and there is no priority classification for any of the customers. So they're
Okay.
served in a FIFO order and there is no limit in the queue, infinite,
Okay.
because it's very unlikely that hockey is overflowed. So I just assume,
Mm-hmm.
and the service providers are working at their full capacity.
Okay.
Okay.
So
So next, yes, sir.
how many server, and then what is your lambda and what is your mu?
Wait, now the data I haven't collect yet because last time
Okay. Okay.
it was Ramat, yeah, Idul Fitri.
Okay.
That's
It
why
was.
it's so packed. I thought that it will be very biased if I took those
Mm.
dates.
Okay.
Okay, so another thing is expected cost MM1 and MMS. So like what you explained before, do you want me to write it down? No need,
It's
yeah.
up to you. Yeah.
Okay, no need because it's basically similar to yours. I will just use the same, assuming the same costs for both of them and compare which result is better from the models I will simulate. I will simulate like around 3 models, I believe.
Mm-hmm.
And the next thing is, okay. I will also use your queuing
Okay.
theory because
This
to
is
assume
the
the worst case scenario for them
worst
to
case.
prepare, yeah, for them to
Yeah,
prepare during,
for the big event.
yes, for the big event. So they can at least, okay, so at least I need to have like 10,
How many server?
10 servers or standby or something like that.
Okay.
Okay, so my next plan is I'm actually going to plan to do data collection this Thursday, 12 May,
Oh,
because
okay.
I just assume it's a random Thursday, right? So it will be very okay. Then Saturday, because I also want to compare on the weekends, because actually in hockey, it they actually have a very big difference on weekends and weekdays. So I will just try to take
Okay.
2 dates
Okay.
and
Good.
develop several models. And then the paper development, I already make a structure. So okay, that's basically it. Then
Great.
I plan on making an Excel quantitative table plus like a simple one for the
Mhm.
if for example if they want to simulate other numbers they can just
Mhm.
so it's basically like your calculator.
Okay.
Yeah, for them like that.
Super. So try to make it. Okay. And if you can publish the paper even in a simple journal, that will be much better. Okay. You will get bonus.
Okay.
Okay.
Okay, thank you, sir.
Good, good. So, Livy, you present this Friday, is that correct?
Yeah.
So, okay, so see you next week, Tuesday. Yeah,
Okay.
Okay, thank you, sir.
Livy this Friday.
Okay.
So Monday we have no class, because of.
Yeah.
Okay.
Mm.
Thank you.